what I would like to do today is work through 2 or 3 of the problems in the text, with you doing significantly more of the work than me. I'm actually out of energy, and I've just discovered that the state is balancing its budget by essentially taking my health insurance apart. So I figure I've done enough work to merit what. Anyway, that is partly true and partly not true. The insurance and the state budget is true, but I'm still going to soldier on. I'm going to give you all that is me. Okay, problem 812 on page 207. Problem 812 on page 207. I think we're agreed now that testing these hypotheses is a 3-step process. And the first step in that process is to define the critical value of the test statistic. That test statistic is a Z statistic in 3 situations. That is, you use a Z statistic when you're comparing X bar and mu, N is large and sigma is known. You use a Z statistic when you're comparing X bar and mu, N is large and sigma is unknown. And you use a Z statistic when you're comparing proportional data. It's only in the situation where N is small and you're comparing a sample mean and a population mean that you use a T statistic. Which of those 4 situations does problem 8.12 describe? And let me read the problem. A random sample of 113 convicted rapists in a state prison completed a program designed to change their attitudes towards women's sex and violence. And I bet that was really successful. They were then released on parole. 58 eventually became repeat sex offenders. Is this recidivism rate significantly different from the rate for all offenders, which is 57%, in that state? Which of the situations are you dealing with here? Are you dealing, first of all, with a situation in which you're comparing a sample mean and a population mean? Let me ask all of you, because this is the theme of today. The theme of today is I'm not taking the exam. You are. And I'm trying to help you. None of you want to see me again. None of you want to see me again 2 weeks from now. And I'm trying to help you out in that regard. This stuff is straightforward if you get the process. And if you're able to make the 4 or 5 decisions in the correct way. Is there anybody who believes that we're comparing here a sample mean and a population mean? Or is it clear to all of you that we're dealing with proportional data? Well, let me phrase it this way then. Is it clear to all of you that we're dealing with proportional data? You've got to do something. You can't just sit there. You got to tell me, yes or no. It's clear. Okay. It's audience participation time. It's time to pay the piper. We're dealing with proportional data. The first step then is to define the critical level of the test statistic Z. And in order to do that, you and I understand that we need 2 pieces of information. You need first of all to know a level of alpha. And the researcher establishes the level of alpha. So let's assume that alpha is 0.05. The next piece of information that you need to know is whether the test is one or two-tailed. And in order to decide whether the test is one or two-tailed, you need to know the research hypothesis. And here we're talking about some relationship between the sample proportion and a population proportion. You have three options here. Option one is that those two scores, those two proportions, will be significantly different. And in that regard, you should look for words in the scenario like different. Yes. Option two would be less than, that P subscript S will be less than P subscript U. And in that regard, you should look for words like lower, fewer, and less than. And option three would be that X bar, or rather P subscript S, is greater than P subscript U. And in that regard, you should look for words like more than, greater, and so on. Let me ask you, what is the research hypothesis in this particular problem? There's one suggestion that the research hypothesis is that P subscript S is not equal to P subscript U. By that I presume you mean significantly different from. How about anybody else?
Yeah.
There are two people now. We have three people. 4, 5, we have 6 people. It's becoming a fashion statement. Is there anybody who thinks something else, or is more importantly, or perhaps as importantly, is there anybody out there who simply doesn't know? You don't know. As you read through this, you read through the problem. Do you have the problem? Well, there's one problem. A random sample of 113 convicted rapists in a state prison system completed a program designed to change their attitudes towards women, sex, and violence before being released on parole. 58 of this sample eventually became repeat sex offenders. Is this recidivism rate significantly different from the rate for all offenders in that state, which is 57%? What do you think the research hypothesis is? Do you think it involves difference? Do you think it involves the idea that the recidivism rate amongst the sample is less than the recidivism rate generally? Or do you think that it involves the proposition that the recidivism rate in the sample is greater than that in the general population? You don't know. What information would you look for?
The lower, the fewer, the less than, and all those words.
Okay, let me read you this statement then from the problem. Is this recidivism rate significantly different from the rate for all offenders?
So it's different?
So you two would now say that the correct option here is option 1.
Yes.
Yes? That we should put here that P subscript S, the recidivism rate in the sample, will be significantly different from the recidivism rate amongst criminals in general. Yeah? Is that to everybody's liking? Is there anybody uncomfortable with that? Anybody who says, I'm not sure of that? Everybody's comfortable, everybody's in place, everybody's found a beverage they like, discovered that the quiche aren't so bad. You'd rather have chips and chili con queso, but there's bucket things that you can now scoop and get like a gallon of whatever dip it is. Those are going to get bigger, you know. You know that's going to happen. Those scooper chips are going to get bigger. It's a given. Yeah. You're going to get cup-sized scoopers. Can you ask a question? What sort of request is it?
Did you say that N is large when it's over 100?
Yes.
100 or more, or just over 100?
100 or more. Yeah, that's any decision about what constitutes a large sample and what constitutes a small sample is to some extent arbitrary. What you're really trying to decide is when do the statistics associated with the sample become stable? How many observations do you have to have in a sample before things like the mean start to stabilize? And that's really a test of, if you have 30 scores, well, let's start lower than that. If you have 5 scores and compute the mean, and now you add a 6th score and recompute the mean, does that 6th score affect the mean profoundly? And clearly it can. If you look at the accumulation of your grade point average, after your first semester, or during your first semester, your performance in any one class could significantly affect your overall GPA. As you accumulate classes, the effect of any one class diminishes. And to a point, in fact, where your overall GPA is pretty resistant to substantial impact from any single class. You can get an I in a class and look at your GPA and it's gone up by like 0.02 of a point. Similarly, you can get a D in a class, look at your GPA and it's gone down like 0.01 of a point. So really the issue between large and small samples is the issue dealing with stability of the statistics associated with those samples. And some researchers would say that occurs with as few as 30 observations. Healy has chosen 100.
So for our purposes of the t-tests, it would be...
Yeah. And you're not going to find on an exam an example of a sample of 101 or a sample of 100 or a sample of 99 or 98. You're going to see clear small samples and clear large samples. But the arbitrary dividing point for Healy is 100. We now decided that if alpha is 0.05 and no, we didn't decide how many tails this test involves. We simply got as far as deciding the research hypothesis. If the research hypothesis is that these two scores will differ, should you conduct a 1 or a 2-tailed test? You should conduct a 2-tailed test because you have to, because this statement of difference can be satisfied, first of all, if x bar is less than mu. That is, if there is negative difference. But it can also be satisfied if x bar is greater than mu. That is, if there's positive difference. So, if the research hypothesis is simply one of difference, you have to test for both positive and negative difference. You have to test both the positive and negative end or tail of the distribution, so that the test should be two-tailed. If alpha is 0.05 and the test is two-tailed, what is the critical z-score? If you can't tell me what it is, where would you find it?
In the appendix.
Plus or minus 1.96.
We have one hopeful soul volunteering plus and minus 1.96. How about anybody else? We have now a confirming vote. Where would you find this out?
Appendix A. Appendix A.
You could go to Appendix A, and you could look for a z-score that has an area beyond z of 0.025. You could look in your notes. That would be a second option. Or you could go to page 193 and look at table 8.1, which is headed Finding Critical Z-Scores for One-Tailed Tests. And even though it says it's dealing with one-tailed tests, it deals with two-tailed tests as well. In the extreme left-hand column, you're given levels of alpha, 0.10, 0.05, 0.01, and 0.001. You can disregard alpha equal to 0.10 and alpha equal to 0.001 and concentrate only on 0.05 and 0.01. You're then told if the test is two-tailed and alpha is 0.05, the critical z-score is plus and minus 1.96. If alpha is 0.01 and it's a two-tailed test, the critical z-score is plus and minus 2.58. You then have two columns that deal with one-tailed tests. Upper tail, where you're testing for positive difference, and lower tail, where you're testing for negative difference. If alpha is 0.01 and it's a one-tailed test testing for positive difference, the critical z-score is plus 1.65. If alpha is 0.01 in that circumstance, the critical z-score is plus 2.33. And likewise, if it's a one-tailed test and you're testing for negative difference, the critical z-scores are minus 1.65 and minus 2.33, respectively. Are there any questions about Table 8.1?
Are we going to have to memorize all these critical z-scores for the test, or are we going
to you can either memorize them, or you can write them on the palm of your hand and look at them. Yeah, you're going to have to memorize them, because if you write them on the palm of your hand and look at them and I see you, I'm going to chop your hand off. If the Hammurabi Code lives nowhere else, it lives here.
We can't bring a table like we were able to.
You can bring Appendix A. Okay. You can bring Appendix A in here. But memorize, it's your choice. You can bring Appendix A. But if you bring Appendix A, you better not have highlighted 4 scores on there. Yeah? Are there any other questions? Two of these scores we encountered in the context of interval estimation, 1.96 and 2.58. So it's simply a matter of adding 2 additional scores to that. Would everybody agree then that the critical z-score here is plus and minus 1.96? If that is the case, here is the decision rule that you have established. Here's the sample distribution of sampling distribution of sample proportions. At the center of that distribution is P subscript U. You have now gone 1.96 standard deviations below the mean and above the mean. And you've isolated 95% of all scores. I will remind you that the height of this curve, the height of this sampling distribution, reflects the frequency with which each of the scores along the x-axis occurs. That is, the most common score along the x-axis is 0 standard deviations, which is associated with the mean. You're looking for rare events, that is, infrequent events. Quasimodo and Elephant Man and the rat-faced boy. While at the other end, you're looking for Denzel Washington and what's his name? Brad Pitt, Sean Connery, that crowd that I'm not at all jealous of. The decision rule is this. If, in order to reject the null hypothesis, when I convert this particular sample proportion into a z-score, it must be in one of these shaded areas. If it is not, if it's in amongst this 95% of scores, we will fail to reject the null hypothesis. Is everybody in agreement with that?
If it's inside
If it's inside this area that I'm now putting lines through, you will fail to reject the null hypothesis. Because everything in there, you have concluded, is not significantly different from P subscript U. It's only beyond these barriers, in this case plus and minus 1.96 standard deviations, that events, scores, are seen to be significantly different from P subscript U. Yeah? So step 2. Step 2 is to compute the critical value, the observed or obtained value of Z. And in order to do that, what formula do I use? I just don't have those notes in front of me. I can't remember what I did, what I said in here yesterday. I can't even remember what I did this morning. I can't remember what I said 2 minutes ago. I'm making this up as I go along. So what is that fourth formula?
PS minus PU over square root all of this. PU times 1 minus PU over N.
That seems to be sort of familiar. Perhaps I'm coming round. In this instance, what is P subscript S? And you don't have to give me a proportion. Tell me what P subscript S is. Give me a value. Give me something. Here's the question. A random sample of 113 convicted rapists in a state prison system completed a program designed to change their attitudes towards women, sex, and violence before being released on parole. Would everybody agree then that N, the size of the sample, is 113? 58 eventually became repeat sex offenders. That is, of that 113, 58 became repeated sex offenders. Is this recidivism rate significantly different from the rate for all offenders in that state, which is 57%? What equals 57%?
PU.
P subscript U. Yes? Let's go back an eon. I indicated to you that proportional data can come in three forms. So three forms of Gozar. Ghostbusters. Proportional data can come in any of three forms. It can obviously come as a proportion. You can be told 0.42 of a sample did something. It can come as a percentage. 42% of a sample did something. And third, it can come in frequency data. 84 out of 200 persons did something. The least likely form is the form you want it in. Proportions. It's simply not part of our language. We typically don't communicate ideas by saying 0.8 of a group did this. 0.6 of the people at the party did this. We're much more comfortable talking about either percentages or using frequency data. 42% of those people asked said that. 19 out of the 28 people in class got this sort of grade. And in fact, in this problem, the proportional data is presented in both forms. P subscript S is presented as frequency data and P subscript U as percentages. Let me ask you first of all, what is P subscript S as a proportion?
58 over 113.
The P subscript S would be 58 divided by 113. And 58 divided by 113 is 0.513, and since we're dealing with data to two decimal places, we could say 0.51, yes? Everybody happy with that? Or is there anybody out there who says, I don't know where that came from? What is the value then of P subscript U?
.57.
What is the value of P subscript U?
0.57.
Any other ideas? P subscript U is 57%. Yes. So we have 58 divided by 113, which is P subscript S, minus P subscript U, which is 57%. When you convert those two scores into proportions, as you must, the first, P subscript S, is 0.51, and the second, P subscript U, is 0.57. Is there anybody uncomfortable with that? Divided then by P subscript U multiplied by 1 minus P subscript U over N. And what are those scores? Divided by the square root of fill in the denominator for me.
57 minus...
No, not 57.
0.57.
0.57. These again, and I'm not being fastidious here, these things have to be proportions.
Minus 0.56.
Why minus 0.56?
Well, 1 minus 0.57.
Multiplied by 1 minus 0.57, which is what?
0.56?
No, it's not.
Sorry.
Will we agree that it's 0.62? No, we wouldn't. We would agree that it's 0.43, I hope. P subscript U, which is 0.57, we decided, multiplied by 1 minus P subscript U, which is 1 minus 0.57, which is 0.43. Yes? Divided by N, which is 113. Are there any questions about how we got to this position? No? So you now set about the plugging and chugging. 0.57 multiplied by 0.43 divided by 113. You take the square root of that. You multiply. I think the answer is 1.29. Minus 1.29. Yes. That is the observed value of Z is minus 1.29. And let me just point something out as a function of a question that was asked of me in the earlier section of this class. Do you understand that these observed Z scores or observed T scores represent a difference? Because the numerator is simply the difference between the sample and the population. So these Z scores are measures of difference between the sample and the population. Yeah, you're not simply translating an individual score into a Z score, but they're measures of difference. Step 3 is to use these two pieces of information to evaluate the null hypothesis. Well, here we are. Z critical is plus and minus 1.96. I believe that the observed Z score was minus 1.29. All those who say you reject the null hypothesis, stick up your hand. no votes for rejecting the null hypothesis, it seems, although there's at least one person wavering. All those who say you fail to reject the null hypothesis. We have some votes for failing to reject the null hypothesis. All those who say, God, I don't know, but on an exam I'm going to fall to my knees and pray to whatever gods there are above that no person lives forever. All those who are going to depend upon divine intervention on the third exam. Nobody's relying on divine intervention. The answer, of course, is that you fail to reject the null hypothesis. If we go back to my attempt to draw a sampling distribution of sample proportions, our decision rule was that in order to reject the null hypothesis, this observed z-score would need to be in one of these two critical regions. It would have to be a rare event. If it fell inside of those boundary markers, that is, if it was simply one of the 95% of scores that we have concluded do not differ significantly from P subscript U, we would fail to reject the null hypothesis. This z-score, observed z-score of minus 1.29, is in that region. It is not a rare event. It is not Quasimodo. It is not Elephant Man. It is not the rat-faced boy. It is not the bearded lady. All of those freaks that used to people the sideshow of circuses weren't really freaks at all. It's not the world's tallest man. So just an ordinary event. You fail to reject the null hypothesis. I don't know. It's more difficult for me to conduct this sort of exercise in here than in a regular classroom. But in part because I have pillars here, that means that behind which some of you hide. I'm afraid to even walk out. Don't know what's waiting for me. This is, I think, a straightforward process. There are a handful of decisions to be made. You need to remember 4 formulae and 4 critical z-scores. And you need to know how to use Appendix B to identify a critical t-score. Given that we're going to look at this situation and then a second situation of hypothesis testing in which you're comparing one sample mean with another sample mean, one can imagine 15, 18 questions dealing with this sort of problem. And each of those scenarios involves 3 questions. What is the critical value? What is the observed value? And then something to do with evaluation of the null hypothesis. These are easy points if you know the process and how to make the decisions and so forth. But if you're sitting there not knowing, then the last exam is going to be a mystery to you. And given the effort I am making, the effort I make, I think, all the time, to have you achieve understanding of these issues, but certainly the effort going through these problems today, If you don't know it, if it's a mystery to you on the third exam, I have no sympathy. I have no sympathy. I'm out to get you. On that day, you know, we're like a married couple who's had a horrible fight. We're in divorce. We're in divorce, and I think you wronged me. Let me ask you to then work through the problems on assignment 6 on WebCT. My understanding from students in this class and in my other class is that those problems are presently unavailable, that they can't be accessed. I will get back to my office at 1 o'clock, and shortly after that time, I will resolve that problem. There are a series of problems like this, labeled assignment 6. My advice to you is simple. You should go through those problems. You should try to work through those problems by yourself. On Tuesday of next week, I will answer whatever questions you have. I will resolve whatever difficulties you have with those problems. Yes. Could you?
On this problem, can we use the 0.25 over n?
Could you hold it down? Because the question that's being asked here may be something that you don't know.
Because on this I have that you could use the 0.25 over n.
The question is in this problem, when you come to computing the observed value of z, is that right? Can you use 0.25 over n as the denominator? Because that's what we did in the context of interval estimation. Yes. When we were talking about interval estimation, p subscript u multiplied by 1 minus p subscript u resolved always to 0.25. But that was so because what we were doing then was trying to estimate p subscript u. Yes? That is, we had no value for p subscript u. But the problem we confronted then was if you're trying to estimate p subscript u and you're called upon to put in a value of p subscript u, what do you do? And I won't go back through the logic of why 0.25, except to say that constituted the most conservative option. That regardless of the true value of p subscript u, the numerator here could not assume a value greater than 0.25. And so we opted for that most conservative of options. You do not do that here because you are given the true value of p subscript u. In this instance, you're told that the recidivism rate for all criminals in the state is 57%. What you're being told there is p subscript u equals 0.57. So the answer to your question is no, this does not resolve to 0.25 over n, and it does not resolve to 0.25 over n because you're given a specific value for p subscript u. Are there any other questions? I then will see you next time, and we will deal with whatever questions you have from assignment 6.